Okay, welcome to Mechanical Systems 1. So this is the first in a series of example problems solving mechanical systems problems. So here we start with some mechanical system and we want to write the governing equation. We don't necessarily need to solve it yet, we just need to write the governing equation. Okay, so to get started, let's just look at the problem we've come up with here. It's two masses, the same mass, two springs, and two dampers. All parameters the same, but we've got two separate displacements, right? So here I've got an x1 and an x2. We need some way to drive the system. Why don't we just add a force? Oh, let's add a force here. Why not? At the top one. This is actually a real system. You can easily make it something that works very much like this if you just connect two pendulums together. So something that looks like this. It's not obvious, but if you measure these angles, these two systems actually act very similarly. Instead of displacements, you've got angles. All right, so let's start to analyze it. So, as with always, I would do column response. How do we begin? I'll give you a moment to scream free body diagram at your computer. Excellent. Everyone sitting around you thinks you're crazy. So, start with the first mass up here. Free body diagram. So, the first mass we've got the x1, the coordinate system there actually identifies it as mass 1. Here we've got my applied force on the top. Oh, and I'll just start calling these F1 and F2 to refer to the spring and the damper. I can also do the same thing for the second mass. Here we're going to have F1 and F2 pushing up. And we're going to have an F3 and an F4. I'm just going to arbitrarily push them as down. Now, so F1 and F2, you'll notice here, are in opposite directions. So they have to be in opposite directions. They have to be in opposite directions because, right, Newton's third law, right? So double check. Yep, that's okay. Okay, so now we need to move on. We've got that, and we need to move on and start looking at our component forces. So we've got a total of 5 different forces, 1, 2, 3, 4, plus the applied force here. So 1, 2, 3, and 4 are the interesting questions now. Free body diagram's there. If we start with our upper two spring and damper here, those are going to look like this. At the top here we have x1. At the bottom here we have x2. Okay. Now, the forces we apply at the top, right? You'll have F1 and F2. Here they're going to have to be acting this way. Opposite the point of contact. And at the bottom, that's my son. At the bottom, you have to have F1 and F2. There we go, like this. All right, so just to double check and make sure I've got my signs correct. F1 opposite, yep. F1 opposite, F2 opposite. Okay, life is good. And we can do the same thing for free body diagrams when I write the bottom springs, right? So here, and the bottom damper here. Right, so here now we're working on these. All right, so here we're going to have a ground at the bottom. All right, so that's just tied to ground. X2, X2. All right. F3, F4, yep, and F3, F4. All right. So again, I just made up these F3s and F4s, and I made up their directions too. But now, you can see once I specify it in one place, it's got to be opposite here, right, at the point of contact. Because on that mass, the point of contact is here, the top of the spring, bottom of the mass. Okay, we've got all that done. Now we can start to write our governing equations. So let's set this aside, and we can start to write governing equations. Fun. Well, it's hard to get this all in shot. I'll have to get better at this. All right, so why don't we start with the mass, with mass 1 here. So no need to think, mx1 double dot is equal to the sum of the forces. Clearly we're going to have F positive because the applied force, F, is in the same direction as the coordinate system. And for the same reason, F1 and F2 will be negative. There we go. We can apply the same approach to get the equation for x2 here. mx2 double dot is equal to F1 plus F2. They are positive in this diagram. And we'll have a negative F3 and negative F4. Alright, so now we just need to figure out what F1, 2, 3, and 4 are. Alright, so coming down here, looking at F1 and F2, they're going to be similar, right? F1 is going to be the spring constant times something. F2 is going to be the damping coefficient times something. So the key is to figure out what the something is. Alright, so here looking at the spring, we see that x1 is pointing in the same direction as the force on that side, so that's going to be positive, x1. And for the same reason, see here x2 is pointing opposite that, so it should be negative, x2. Alright, and we can just basically do the same thing for the damping coefficient, right? There's damping. For those of you who haven't started screaming at the computer, don't forget your dots, please do so now. Don't forget your dots. Excellent. Make sure everyone around you can hear you screaming at your computer. It's the only correct way to do this. Okay, so F3, apply the same approach. The spring stiffness is still just K. In this case, all the spring stiffnesses are K. They could have easily been a K1 and a K2, in which case we'd have to treat them separately. But in this case, they're all the same. So easy peasy. Okay, so F3, we see X2 is pointing in the positive direction, or is pointing the same direction as F3, so yeah, X2 is positive. And then down here we see there is no other motion, so that's just minus 0, or you can just leave it off if you want. Alright, F4, B times X2 minus 0. Don't forget your dots. Excellent. Excellent. Yeah, yell it with me now. Alright, so now we just back substitute. We just need to jam all these into here, and we're good to go. mx1 double dot is equal to F, alright. Here we have a negative F1, so what we're going to find is, yeah, when we substitute in, I'm going to go ahead and skip a step here. So once you substitute this in for F1, you'll have negative kx1 plus kx2. Don't forget to distribute this negative across that. Should give you this. And similarly, when we substitute into F2 for the damper, we're going to have negative bx1 dot plus bx2 dot. Okay? I can, just to make that look nicer, I like to organize all of my x1s together. That sounds like a good idea. Then on the right-hand side, interestingly enough, we see F, the forcing term. That's the input to the system, is the driving force that's going to make this whole thing move. All right, and then let's write some other terms. That is, we're still left with the the bx2 dot and the kx2. There we go. So what we see is, in this system, the motion of x1, that is mass 1, this first mass here, is determined by, oops, went off shot there, sorry about that. The motion of mass 1 is determined by this input force, but also by whatever mass 2 is doing. So these systems are inherently coupled, which makes them interesting. So this is my answer for the first mass. All right, next to keep going. All right, now we just need to substitute to get rid of all this. Now this is actually going to be even more interesting. So starting with F1 and F2, this time we see they're positive, so the signs are going to be flipped, because here in X1 there was a negative. Here there's no negative, so now we're going to see the signs down here will be flipped of what they were here. So now we've just got a K, X1 minus K, X2, whoops, silly, K, X2, minus, or excuse me, plus, I just went on a whole tangent about how it's going to be opposite, X1 minus X2 dot, there we go. So that takes care of F1 and F2. Now we also need F3 and F4, so those are just X2s. So here we now see negative K, X2, negative B, X2 dot. Reorganize that, and here's what we get. All right, let's just make sure I got that right. So there's only a single mass, so that's correct. There are two stiffnesses with an X2 coefficient. They have the same term, so those will combine to give me this term right here once I move them to the right-hand side, or the left-hand side, excuse me. I swear I know my right from my left. The same thing is going to happen with the damping terms here. So this fella here combines with this fella here, and we get this. And so this is my answer for the second one. Now, a lot of you are going to be asking, how did I know I can stop here? How do I know I don't have to substitute out x1 or x2 and just write it in terms of one output variable? On a midterm or on a quiz, I will have to be very specific about what I want from you in that term, in that sense. So this problem is tricky enough, actually, that's back substitution is hard enough that for this problem, this is far enough. I wouldn't ask you to go past this. The easiest way to do that is with Laplace transforms, interestingly enough. So, stay tuned for your controls class next. All right, anyway, so there it is. That's Mechanical Systems 1. I'll scan this, and you will be able to download it along with this video. Thanks for your attention.